An exponential function is when you repeatedly multiply by the same thing, called a base. There's two different types of exponential functions that we've looked at. Exponential growth, when you repeatedly multiply by a number bigger than 1, is going to cause your values to grow slowly and then quickly. Exponential decay, when you multiply repeatedly by a number less than 1, is going to drop quickly and then slowly. So now that we know what an exponential function is, let's see if we can do exponential regression. Let's see if we can take some data and find an exponential function that's a good model for the data. The first example we're going to look at is looking at the growth of a certain store over the course of time. You can see that at the beginning of the store's growth, it's growing relatively slowly at first. It's increasing from year to year by, 13 stores the first year, 21 stores the second year. But by the end of this table, we see that it's growing by over 200 stores per year. And that makes a lot of sense, right? Because when you first start out as a store, your growth is going to be kind of slow. You probably begin in just one small location, but the better you do, you start to spread out more to other locations, and then the better they all do, the faster and the easier it is to grow even faster, right? This is the idea that we call going viral, right, on the internet. Somebody posts something silly on TikTok or whatever, and a few buddies like it and share it, and then a few more people for each of them likes it and shares it, and before you know it, it's got 1 million views on the internet. So let's make a table and look at the scatter plot. I'm just going to use this embedded Desmos calculator right here. I'm going to make my table. Notice we're not going to type in the actual year. Well, for 1986, we're just going to type the number 1. This is the first year, and then this is the second year, and the third year, and so on. Because we don't really care about what year it happened. We just care about the number of total years. If you count these up, you got 1, 2, 3, 4, 5, 6, 7, 8, 9 years. So I'll go down to year 9. All right, I hit my little magnifying glass so that I can zoom in on the data, and you can see this does look like exponential growth. It's growing slowly at the beginning and quickly at the end. I'm going to press my add regression button, and the default is going to be to make a linear regression. This is not a terrible fit. The R-squared value is 0.79, but if I change this from linear to exponential, it's going to be almost perfect. The R-squared value is now 0.9978. One option you have here when you do this is to check what's called log mode. I won't get into the details of that now, but just all you need to know is that that's just a different way for the computer to calculate this equation. And I've found it in my experience that when you have like multiple choice tests and things like that, typically the answer that's given is the one given by log mode. So as a default, I'm going to check that box. It's going to just slightly change my answer. Still a very good value. So what's the equation for the exponential curve of best fit? It's this right here. I'm going to export that and copy it. And I want you to notice the format of this equation. Instead of it being like y equals mx plus b, like a linear function, or having an x squared in it, like a quadratic function, exponential functions have something raised to the power of x. That's what exponential functions are. How would we figure out the number of stores, or rather predict the number of stores in 1996? Well, if you look at your table, year 9 in our table was 1994, so that would mean year 11 would be 1996. So again, there's two different ways I could get the answer. I could use my graph. It's a little bit hard to see here. I might need to zoom out slightly to get to year 11. One little trick on Desmos, notice what happens to my cursor when I hold down the shift button. I'm holding that shift on my keyboard, and you'll see that when I do that, it changes the pointer tool to a diagonal arrow. Well, if I hold down shift and then move my cursor over toward the y-axis, notice the y-axis gets highlighted blue, and my cursor turns to a vertical arrow. Continuing to hold down shift, I can now click and drag down the y-axis. This is a very convenient way to kind of adjust my graph. I can keep holding it down and drag over the x-axis as well. And I can this way get the window just the way I want it. So I can go to where x is 11, and the predicted number of stores is 1,695. The other way I could do it is I could take my function and replace the x with 11. And that gives you the same answer. Let's look at another example. This time we're looking at soup that's left out on the countertop. What's going to happen to the temperature of it? Well, it starts out very hot, 180.2 degrees. But as time goes by, as expected, the temperature drops. Now, how is it going to drop? Is it going to drop by the same amount per minute? Well, no. If that happened, eventually the soup would be absolute zero, right? It would go all the way down to where the atoms aren't even moving anymore. No, what happens is the temperature drops quickly at the beginning, and then it starts to level off. And that's what we call exponential decay. So let's make our table. Let's see if we can make a best fit equation for it. I hit my magnifying glass, and this actually looks a lot more linear than what we might expect, but we know that as time goes by, this is not going to continue following a linear pattern. It is going to level off eventually at room temperature probably, right? So we'll click the Add Regression button. We're going to switch to exponential. We're going to press log mode. And you can see the r-squared value is 0.9879, very high. So this right here, if I press export, this is the exponential best fit equation. One last example, we're looking at the population of single-celled organisms in a petri dish. Hopefully these are good organisms, not bad ones. But you could probably expect that the growth of these organisms is going to be exponential. They're going to be multiplying, right? And when you only have a few organisms at the beginning, they don't multiply that quickly. But the more organisms you get, the faster they multiply, right? So this is going to be exponential growth. Let's make our table. And I need to be careful here. If you notice, it's counting by twos, except it skips over 14. And that's because we're going to be calculating a prediction at 14 hours. So got to make sure I skip over 14. Press my magnifying glass. There's my exponential growth curve. It's growing slowly and then quickly. To make my regression, I press this little Add Regression button. The r-squared value is 0.88 for linear. Let's switch to exponential. It's almost 100%, right? 0.9936. So this is my equation. I'm just going to export it and copy it and put it right there. How many organisms would we expect after 14 hours? The hours is x. So I want to know when x is 14, this function is going to predict the number of organisms. So I could just follow the curve when x is 14. There are about 194, almost 195 organisms, right? I'll round it up since it's 0.5. 195 organisms. The other way I could do it is I could replace this x value with 14. 195. The last question is, how many hours do you expect it to take until there are 1,000 organisms? Notice this time we're looking for the number of hours. We're looking for x. We don't know what x is. We don't know how many hours there are. What we know is that the number of organisms. That's the y value. Y is the number of organisms. So I want to know when the y value is 1,000, what would the x value be? So if I look at my y-axis here, 1,000 is way up high, up above my window, right? So I'm going to hold down Shift on my keyboard. While I'm holding it down, I'm going to move my cursor over to the y-axis until it highlights blue. Once I get to 1,000, I'm off the screen a bit, so I'll also drag over the x-axis. And now I can see, I can get it pretty close. It's about 25 or 26. I'm going to round up to 26 hours. The other way I could do it is I could replace my y value with 1,000 here. And you'll get the same answer, right? Zoom in a bit here and you can see it's going to be almost 26, between 25 and 26.